Have you ever wondered how planes fly or how a spray bottle works? It's all thanks to Bernoulli
At
equations.
first, let's talk about some basic things that will be needed in describing the Bernoulli equations. In fluid dynamics means the fluid is moving, it's not in the static position. So, in the fluid dynamics, the fluid that is considered for our description must be ideal. So, the fluid is considered as ideal fluid. So here one thing says the fluid must be ideal. There are some characteristics of this ideal fluid which is different from the normal fluid. This ideal fluid fulfill these requirements, but the normal fluid does not require these requirements. So let's see the characteristics of this ideal fluid. The fluid must be incompressible, means the density is not changed for anywhere the fluid is, so no change in the density. The density remains same through the whole fluid. Then second thing is non-viscous. The fluid must be non-viscous. Non-viscous means no friction between layers. Suppose a car is moving upon a road, then the wheels of the car will face some viscous force, a friction force, which is occurs in the solid materials. Similarly, in the fluid, there will also occur some viscous force, but the friction is not for the our ideal fluid. The friction force works at the non-ideal fluid, so this ideal fluid must be non-viscous. Then, as it is not static, it is dynamics, means it is moving, so it is irrotational, means the omega is equals to 0, it will be not rotate. So where the omega is angular motion, so here the angular motion will be 0, it will flow but it will not rotate. And the another or second condition is the flow must be steady flow or streamline flow. Let's understand what is steady flow means. It at any point in space the velocity v of fluid molecules every molecules remains constant with the time. Means if the suppose it is a pipe of a fluid that is flow under through this pipe, and this a is denoted as any specific point. Here all the water molecules pass through this point. When all these molecules pass through this point, they have a certain velocity. Suppose it is v1. This v1 velocity is for all these points when they pass in this area. So suppose this point is C and this molecules is C and this molecules is D, etc. So when these C molecules pass through this A area, it will have a certain velocity of v1, and the D or molecules when pass through area of A, it will also have the same velocity of v1. Means all the particles or molecules of fluid which passes in this same area, they will have the same velocity of v1. This line means these things. Then suppose B is the another area, here the velocity of the particles will be v2, as here area changed, so here velocity will be also changed. Suppose these same molecules will come here and they will pass through this area one by one, then they will also have the same velocity of v2. Suppose this is a molecule, it will the same velocity as v2 when it passes the area B. Then the second molecule also have the same velocity, third molecule will have the same velocity when they pass in the same area. And another thing is any particle follows the path of the previous particle. Means suppose this is our first particle, it will go through this way, and behind this there will be another particle, so this second particle will follow this previous. This is the previous for second term, so this second will be follow the same path of the previous particle. So when the first particle move in this way, so the second particle also move through this way with the same velocity. Steady flow means these things. In the fluid dynamics, the fluid must be ideal fluid and the flow of the fluid must be steady flow or streamline flow. These two things are the basic condition in fluid dynamics. Now let's understand how the direction of any point, the velocity of directions is considered. Means suppose this is a point A, here the velocity direction of the fluid particles is VA and it is directed as towards like this, means it is the tangent of this A point. So if we want to find out the direction of velocity of any point, then we have to draw a tangent at that particular point, and with the tangent we will get the direction of the velocity. Similarly, this is the point B, and here the velocity will be VB. So if we want to find out the direction of this VB, so we have to draw a tangent upon this B point, then we will get the direction of this fluid particle. So there may be a question, suppose it is a tunnel, so there may be a question that the ever two streamline intersects means like this. Suppose this is a single particle of any fluid, ever this two streamline intersect, suppose this is one particle or molecules of any fluid, so the direction of this will be like this, and the second particle will be here, and if they intersect, then these things will looks like this. So look at this point. If we consider at this point only one single particle, then it is seen that for this one particle there are two directions of the velocity. It is never possible to have these two directions of velocity for one single particle, as they never intersect with each other. So never two streamline intersect. Suppose it is a streamline and it is another streamline, here two streamline never intersects with each other. Now let's see the equation of continuity. Suppose this is a tube or tunnel, and this is a cross sectional area of suppose A, and this is another cross sectional area, it is A2 and it is A1. Suppose water is flowed through the tube and this A1 area is smaller than this A2. Have you ever noticed these things at the time of watering your garden? Suppose this is your garden and this is water pipeline, and you have to give water in your garden, but this pipeline is small than the distance, so you have to reach this water in your garden. Then what will you do? You will press the pipe and divide it into two small section, and this way the speed of the water will be increased and it will reach to the garden. So here what you have done for increasing the velocity, you have divide the area into two small portion, means you decrease your area and thus the velocity increase. So here will also happens the same things. Here A1 area is small and A2 area is big, so the velocity of this area will be V1, which is bigger than the velocity of A2 area V2, but the rate of flow will be remain same. Here the volume of water entering through this A1 area, the same volume of water will be leaving this A2 area in a unit time. As it is constant, so the rate of flow of the fluid will be A into V. Here A is the area and V is the velocity, and this portion remains constant. Why constant? If you visually think about this, here the area is small and velocity is high, so here the multiplication of AV will be equals to this A2 V2, because here area is small but area is big but velocity is small. So from these things we can write that A1 V1 equals to A2 V2, means if this A1 decrease then this V1 increase, and if this A2 increase then this V1 decrease. This is how they remain constant. From this relation it can be said that the amount of fluid entering a pipe per unit time must equal the amount of leaving. It is must remember that per unit time means there is a specific unit time at the time where the volume of water entering is equals the amount of water leaving. This also be understand by the use of conservation of mass, and these things is called the equation of continuity. This is called the equation of continuity. This equation of continuity can be also proved according to the conservation of mass, means the mass of fluid that enters at time del t equals to mass of fluid that leaves that in time del t. These two things are equal, and from these equations we can also prove the equation of continuity. If you want to saw the proof, then ask me in the comment section, I will give the proof. Now using the equation of continuity we will solve a mathematical problem. From the equation of continuity we got the equation as A1 V1 equals to A to V2, where A is the area and V is the velocity. In this question, here said that this is a pipe and we took two cross-sectional area. This is one first cross-sectional area, this is second cross-sectional area. Here said that the radius of this section, circular section, is 1 millimeter, and for this area cross-section is 2 millimeter. Here the velocity v1 equals to 2 meter per second, and we have to find out the v2 of this cross-sectional area. So according to this equation we can solve the problem. Now let's solve. For this circular area we have a1 as pi r square. Pi, here I is 1, so I r square, pi r square into v1 means 2 meter per second, equals to a2 means this areas, this portion area, which is pi r square, r here 2 r square into v2. We have to find this v2. So if we calculate from these things, this pi cancel out, and from this if we find, then we will got the v2 as 0.5 meter per second. So the velocity of this area will be 0.5 meter per second. From these things we also see that here the area is small and the velocity is big, and for this here area, here the area is big but the velocity is small, and this is remains as constant for both area. Now let's see our most important thing, the Bernoulli theorem. So proving this Bernoulli theorem, two conditions must be fulfilled at first. One is the fluid must be ideal, and second is it must be streamline flow. After completing these two fulfilling these two conditions, then we will go forward for the proving of Bernoulli theorem. Now first let's see what does this theorem states. This Bernoulli's theorem states that in a steady, incompressible and frictionless flow of fluid, we already have read these characteristics in the portion of ideal fluid. So incompressible of fluid, the total mechanical energy means of the pressure energy, kinetic energy and potential energy, the total mechanical energy along the streamline is constant. Suppose it is a canal and here is a fluid flow. So in this portion we see that if some particles of water will be flowed through this and this will push inside the pipe. So here works a pressure energy. Then as this is fluid dynamics and here the fluid is moving, so it will also have a specific velocity. For the velocity will got a kinetic energy, and it is, suppose the height from the ground is h, so the fluid must be a potential energy. So all these three mechanical energy of the streamline will remains constant. Let's say the visual of this states. Suppose P is for pressure energy, and for kinetic energy it is half rho v square, and for potential energy it is rho g and h, equals to, according to this Bernoulli's theorem, this will be constant. Now let's prove how these three things remains constant. Suppose this is a small portion of streamline flow of an ideal fluid. Here we will consider the fluid contained in AB. At first the fluid will be contained in this portion AB, and in the time interval of del t, after passing the time interval del t, the fluid moves section A prime B prime. As this fluid is not static, it is moving, so at first they are in the portion of AB, and after del t time they move some distance, so they reaches from A prime to B prime. So here must be a velocity v1, and for this portion the velocity will be v2, and the pressure of this point will be p1, and pressure for this point will be p2. Area of this point a2, area of first point a1, and this portion which the fluid travels at del t time, that will be, this distance will be v1 del t, and for this distance will be v2 del t. This is the moving distance of the flowing fluid. From the work energy theorem we know that the work done by all the forces is equals to difference of potential, difference of kinetic energy, means the difference of kinetic energy of the initial and the final. This is equals to the work done by the all forces. With this work energy theorem, we will prove the Bernoulli's theorem. At first, see that here the fluid entering this pipe, here this fluid creates a pressure upon this point. So as the fluid creates pressure, so here we'll find the work done by fluid pressure. So this will be denoted as WF. It will be WA prime plus WB B prime, because the first layer stands this A point and after delta time it moves at A prime. So here certain works is done by the fluid, and the second layer or last layer will be at the first B point, and after delta it reaches B prime. So the second work done will be B and B prime. We know that W work equals to F force into distance, and force equals to pressure into area. So from here we can write that W equals to pressure into area into distance. So for work done by A and A prime, here we'll write the pressure P1 for this portion. This P1 will be activated. So pressure P1, and here this area is A1, and the distance, this is V1 del T. This moves from A to A prime in del T time. This distance is considered as V1 del T. Plus for this portion, the pressure will be P2, area will be A2, and the distance will be V2 del T. But look at this. Here the pressure is working towards this direction, but here the pressure is working in the opposite direction. So here we will use this minus sign. If we further calculate, then we will get P1 A1 V1 del T minus P2 A2 V2 del T. From the equation of continuity, we know that A1 V1 equals to A2 V2. From the mass equation, we know that del M equals to rho into volume. This is the density of the fluid. So from here we can write rho into here volume means A1 V1 del T. This is the distance of this, and the area of this portion is A1, and this distance is V1 del T. So here this works as length, and from after multiplying this we get the volume. And from the equation of continuity, we can write from instead of A1 V1 A2 V2 into del T. So this and this equals to same. Now we will put these things in this our required equation. Here P1, and instead of A1 V1 del T, A1 V1 del T, we can write del M divided by rho. Del M divided by rho minus P2, and instead of A2 V2 and del T, we can write del M divided by rho. To del M divided by rho. So from here we can took the common del M by rho, and here remains P2 minus P1. So this is the work done by fluid pressure. Now our second term is the work done by gravity. So that the work done by gravity is equals to minus del U. Here this fluid is upon a certain height. Here this area is upon a certain height H1, and here H2. So if we divide these things into initial, U initial and U final, then we will get U initial as the initial portion AB. We considered the initial fluid contained in the AB. So internal force of UAB minus our final destination is A prime B prime. So U of A prime and B prime. Now let's further break down this UAB. UAB, let's see here. UAB means this portion. If you notice that here are two portions, A and A prime, then A prime to B. So we can write U of AB as U of A prime plus U of A prime B minus U of A prime B prime. U of A prime B prime means this portion. This portion can be also divided into two portions, U of A prime B and U of B and B prime. So we'll further divide this into two portions, U of A prime B plus U of B B prime. We'll use bracket as here is a minus sign. So U of A prime plus U of A prime B minus U of A prime B minus U of B B prime. and this a prime b will be cancelled out, and we will get u a prime minus u of b prime, which can be written as, we know the equation of this internal energy or potential energy, del mg h1. Why we use here h1? Because we considered this first portion fluid is situated at the height of h1 and the second portion fluid situated at the height of h2. So for the potential energy of u a and a prime, here we will use the h1 as height, and for u b prime it will be del m h g h2, and if we took the common, then we'll get del mg h1 minus h2. And from the work energy theorem, we know that work done by all forces is equals to difference of kinetic energy. So here work done by the pressure and the gravity will be equals to the difference between these 2 points kinetic energy. So from this theorem we can write the work done by fluid pressure and the work done by the gravity is equals to the potential energy of final minus potential energy of initial. So what is this final? It equals to potential energy of a prime b prime minus potential energy of AB, because this is the initial position and this is the final position. According to our potential energy, we can also break down into these 2 points, which is, look at this figure, this here we written a prime b prime. So we can divide this into potential energy of a prime b plus potential energy of b prime minus potential energy of AB, means this point to this point. If we break down this, we can write potential energy of A and A prime plus potential energy of A prime B. If we remove the bracket, then we'll get A prime B plus potential energy of B prime minus potential energy of A prime minus potential energy of A prime B. So this A prime B 2 terms will be cancelled out, and our final result will be potential energy of B prime minus potential energy of A prime. So from our previous equation, we can write this work done by the fluid as del m by rho to P1 minus P2 plus work done by the gravity force, which we have find that del mg into h1 minus h2, and in our right side here will be potential energy, kinetic energy of b prime, which is half del m v2 square. Here see, for the b and b prime the velocity is v2, and for a and a prime the velocity is v1. So here for kinetic energy of a and a prime, this is half del m v1 square. Now if we multiply this whole equations into rho divided by del m, then this all the del m will be cancelled out, and this, if we multiply with rho, then for this term rho will be cancelled out. Here remains p1 minus p2 plus rho multiplied by rho g into h1 minus h2 equals to half rho v2 square plus half rho v1 square. And from this equation we can write p1 minus p2 plus rho g h1 minus rho g h2 equals to half rho v2 square plus half rho v1 square. Sorry, here as this is, there will be minus sign, so we do a mistake here, we will also have to use minus sign. Now the v1 h1 p1 portion will be one sided, and the second v2 h2 will be another side. We will rearrange it. So p1 and this portion will be took in the left side, so this will be plus half rho v1 square, and this portion remains here plus rho g h1 equals to, we took the p2 in our right side, so p2 plus this kinetic energy half rho v2 square, this potential energy plus rho g h2. Here see that the 2 points in total energy is equals to same, means the total mechanical energy of this portion is equals to the total mechanical energy of this portion. So it simplifies that the p plus half rho v square plus rho g h equals to constant. This is our Bernoulli equation. As the sum of these three terms remains constant according to our Bernoulli equations, and we also have proved this equation, then from this equation we can observe that if the pressure is high, then the velocity will be low, as the total term summation of this total term will be constant, and if the pressure is high, then the velocity will be low. Using this principle, the plane flies in the air. Spraying in the bottle also use this principle. Now let's think about the airplane wings. The airplane wings is something like this curved. So when the air moves faster over this curved top, so here is low pressure. And as here is low pressure, so the velocity will be high. And at the lower, the velocity will be low of the air, and so the pressure will be high. As at the lower the pressure is high, and in the universe everything want to grow from high to low, so this wings also wants to go from high pressure to low pressure, and that's why it's lifted up. The air moves faster over a plane's wings, causing low pressure on top and lifting it into the sky. This is how the plane flies in the sky freely. Now if you have any questions upon these Bernoulli equations, then please ask me in the comment section. Thank you.